Do you have a frequency or time-sensitive application? Have you ever wanted to measure the stability of your system to ensure reliability? Hi, welcome to the lab. My name's Chris Higgins. I'm an applications engineer from Beverly, Massachusetts with our Atomic Clock Group. And today, we're going to be looking at the 53100 Phase Noise Analyzer test set. What I have here in front of me is what you get in the box. If you open it up, you'll see the certificate of the conformance, which we'll take a look at. And then beneath this, the phase noise test set itself. Let's take a quick look at this though, as it's the first thing you're going to want to look at when you unbox. First page, you'll see a certificate of conformance. But then these reports are going to give you a great insight on how this unit actually performed at the factory. You'll get to see the phase noise floor, along with these great, wonderful tests that it passed, and the phase noise performance, as well as the AM noise. And you'll get to see a little bit of what the test scripts that are run at the factory, what they actually give you. If you have an internal reference model like I have here, you'll also get this calibration report, which does a couple of tests on the internal oscillator, which is running at 100 megahertz on the inside, ADEV and phase noise. You'll also get this spiffy certificate of calibration, which you'll be able to use if you ever send it back to the factory and get it recalibrated. So in the box, you'll see the phase noise analyzer, as well as all of the cables and connectors you'll need. Also included is a USB thumb drive, which includes TimeLab, the GUI that we use to talk, communicate to the phase noise analyzer, as well as view all of the results. Let's take a look at the box itself. So on the back, you'll see your serial number and your model number. This one that I have right here is an internal reference version. We'll talk a little bit about that later. But this one comes with a calibration sticker for the internal oscillators, as well as these connectors on the front installed in this way so that you can fully utilize the internal references. What we'll be measuring today is Microchip's CSAC, or chip scale atomic clock. It's a super low power embedded atomic oscillator. Now all I have for this setup is the 53100, power going into the CSAC, and 10 megahertz coming out of the CSAC and into the DUT. Our reference ports right here take the internal 100 megahertz oscillator and feed that into our system. Now that everything's set up, let's go into TimeLab and start looking at our measurements. All right, now that we're in TimeLab, let's get a measurement started. To start a measurement, either go to the Acquire tab and click the 53100, or alternatively, you can just press space. It's a lot quicker. Let's start a 15-minute test real quick. And one of the important things you want to do before starting your measurement is make sure that your references are set up correctly. Like I said, we've got the internal reference version, but if you have, say, a singular OCXO or another atomic clock and you're only using one reference, make sure that you select the correct configuration and change your front panel connectors to reflect the picture in this window. Let's start our measurement. And as it's initializing, I like to mention that all of the measurements that the 53100 does, it does them all at the same exact time. So your phase noise, your Allen deviation, your frequency difference, all of these things are at the same time measured. And you can switch between these plots by clicking on measurement and going to the measurement that you want. So here's our frequency difference. Here's our Allen deviation or ADEV. Here's our AM noise. And here's our phase difference. Now to switch between these really quickly, they all have keyboard shortcuts if you saw them to the right. And that's really helpful if you're, say, in an engineering lab and you want a quick switch between phase noise, frequency difference, ADEV. Super quick to learn these shortcuts so that you can move around a little bit faster. Now, while the test is running, I like to mention one of the main advantages of using a system like this is that the close-in phase noise measurements are really, really good. We can get down to like 1 millihertz on this, which is really important in communication applications or in atomic oscillators like what we're measuring right here. All right, now that I've stopped our measurement, let's take a look at what we actually got. So this phase noise plot has gotten about to 1/10 of a hertz, and I think that's just enough for our purposes here today. But you may notice this shaded area underneath the trace itself, and this is the phase noise floor of the instrument. And the way you lower this is either adding more references or getting a higher quality reference. But you want a good barrier in between your trace and that noise floor itself. But let's switch over to Allen deviation real quick. And let's say you want to check your stability at a certain offset. Say you want to check your 1 second stability. Now you can either check that over here on the chart, Or you can move your spot cursor to 10 seconds or 5 seconds or say 0.2 seconds. You can move this back and forth. If you want a little more data shown on this bottom legend here, you can actually go to the legend, hit select, and let's say you want to see the input amplitude of your device under test, or say the date and time if you want to compare different tests against each other. You can all change that right here. And that's all for today. If you're interested in this phase noise analyzer and you want to know more about measurements, how to do more advanced measurements, there's an app note with a link in the description. Thanks for watching. See you next time in the lab.